So just to double check, we totally got done with the word problems about the boxes in this hour, right? I know there was, I think there was 1 hour that did it in a second. And I would expect to see a box problem on the test. I mean, we did kind of 3 examples of this because we talked about the designing a box and finding where you should use the X value, whatever it is, what that X should be. Then we talked about one that said, okay, once you found X, now go back and figure out what all the dimensions of the box would be. And then that final one was finding that maximum volume. So, any of those, I would expect to see at least one, since there were 3 different problems that we looked at, basically. And then, as we move on, it says, just as any 2 points in the Cartesian plane with different X values and different Y values determine a unique slant line and its related linear function, any 3 non-collinear points with different X values determine a quadratic function. So, you learned in geometry this thing called the point line plane postulate, and it said, you have 2 points, you can draw a line. And that meant if we know that we have 2 points, we can just find the slope, we can write an equation for it. It'd be kind of silly to use linear regression if it was 2 points, but we could use linear regression. So this is now saying, if you've got 3 points, and maybe you don't want to take the time to look at them to see if they show up as a line, you're guaranteed with 3 points, take 1 away, 3 minus 1 is 2, that you'll be able to write that. So any 3 non-collinear points with different X values will determine a quadratic function of the degree 2 function. In general, n plus 1 points positioned with sufficient generality determine a polynomial function of degree n. Now that doesn't mean if we see, oh, they gave us 5 points, let's do a coordinate. We still know we should take a look at it. It could be that they're all lined up perfectly for a line or really close to linear. So this is kind of a backup point. You're looking at the points, you're not seeing any general cubic, quartic, quadratic, any of those things, then well, if I have 6 points, 6 minus 1 is 5, maybe I better try and do a quintic regression on this. And we're going to find that our graphing calculator doesn't have an endless supply of regressions on there, but we also know that anything that's odd kind of behaves like a cubic, and so we could kind of use that when we get to the higher powers, the higher degrees. And that process of fitting a polynomial of degree n to n plus 1 points is called nothing. I wondered about this last night. Did it finally move? Yeah. Last night somebody came in and asked about something in campus, and it took my computer more than 5 minutes to let us see what we needed to see. So, in general, instead of just calling things regression forever, the fancy math name for it is the polynomial interpolation. So, you don't have time to take a look at them? Well, you should always make time. You should always at least take a quick peek at the stat plot. But if you're looking at the stat plot and you're saying, this doesn't fit any shape that I can even remember, then what you can always do is say, hey, I've got 1, 2, 3, 4 points here. 4 minus 1 is 3. I can get a cubic to fit this. It's going to work. So exploration 2 involves 2 polynomial interpolation problems. So that's what we're going to look at next. And with these, they're saying, skip the stat plot. We're telling you what we want you to do. We're saying use cubic regression to fit a curve through the 4 points given in the table. So we want to go ahead and get those into your tables. The graphic calculator. I'm trying to pose a couple of things here. Maybe that'll speed this thing up this morning. And because I knew I was going to have to record one of these lessons today, I just went ahead and put those 2 into this one, those 2. So take a minute or 2 here and go ahead and get those 4 points. Here's those 2. X is in this 1. Y is in this 2. And we they flat out told us cubic regression. So we go to stats and calculate. And like I said, there's not an endless supply of regressions here, but we can see we have linear, we have quadratic, cubic, quartic, linear regression, natural log regression. Then we have exponential and power regression, logistic regression, the sinusoidal regressions. And then they say, you can try a manual fit. So we have things available to us here. It is not endless. The ones that we're going to work with in here are usually as high as maybe 40. We don't really go that high anymore. So we want to do the cubic regression, which is number 6. And I want to make sure that this is using the two lists that I have this in. Now, if you have either one of my older yellow calculators or you have an older model calculator, it's going to use list 1 and list 2 first anyway. So you probably don't have to put anything behind it. You can just go ahead and go to calculate, hit enter on the older ones. And there it is. It's showing us right up here. Here's your model, ax cubed plus bx squared plus cx plus d. And these are the values that you should use for A, B, C, and D. And we notice there's not a lowercase r. There's not a correlation coefficient. And that's because once we get past linear correlation, they expect that we're going to look at this and go, hey, if r squared is 1 and I take the square root of both sides, that's 1. That's a perfect fit. And that's what we were talking about in the paragraph that was talking about interpolation, is if you just take the number of points and subtract 1, it's going to be a perfect fit. It will. It'll work every time for interpolation. So now we need to write down all those obnoxious decimals that we saw. For number 1, let's see. Glasses are there. Use cubic regression to fit a curve. It doesn't say it has to be a polynomial function, but we're always safe if we use f of x, g of x, something along those lines. And it was 0.006 x cubed. Then we had 0.018 x squared minus 0.501 x plus 0.977. And again, the big deal about that was that r squared equaled 1. So this means this is a perfect fit. Being a perfect fit mathematically doesn't mean it's the best model for the job. The best model for the job is always taking a look at the stat plots, noticing if there's a pattern, and if there is, then fitting it to the appropriate model. But if you don't have a choice, like in this one, that said use cubic regression, then that's just what you do. And that's what we're going to have you do on the test too. So we're going to flat out say we want to see you do this regression. So there's no question that everybody's going to get the right answer as they go through. And number 2 says, well, we've got 1, 2, 3, 4, 5 points. You don't want to bother with the stat plot. 5 minus 1 is 4. We use quartic regression. Ought to be a perfect fit right through those points. So again, here's your list 1, here's your list 2. You can either rewrite what you had in list 1 and list 2, because we're not going to use those anymore. Or I put these in list 3 and list 4 because I had to use that big point. Go ahead and get those points in. I can see you're already doing the regression, which is great. That means you're feeling really comfortable with this. So, stats, calculate, and this time we're going after quartic regression, which is number 7. And now, because I knew I was going to have to do this, I put my lists in list 3 and list 4, so I would have to change those second number 3. second, number 4. If I were you, I just would have rewritten L1 and L2. And again, if you've done that, all you have to do is hit calculate. It's the only data that's in there, so the calculator will take care of it for you. So this one, notice it doesn't spell it all out for us anymore. It says, we told you what it was for cubic. You ought to be able to figure out that it's going to be ax to the 4th, bx to the 3rd, cx squared, etc. We're not going to give you all of that anymore. But we get nicer numbers for a few of these. You know, we've got an a of negative 0.375, b, c, d, e works out perfect. And again, r squared is 1. So if you take the square root of both sides, this is a perfect fit. Again, not maybe the best mathematical model. We would have to actually take a look at the data to see that. Does it make sense for what the data has? I'm going to name this one g of x just so we have something a little different. So that one was negative 0.375 x to the 4th plus 6.917 x to the 3rd minus 44.125 x squared. Oops. That big blob almost looked like this. Right, that would be bigger. And then we had plus 116.583x and a perfect minus 1. And again, the question is, how good is the fit in each case? So we want to show r squared equals 1. And that means we have a perfect fit. Now, why wouldn't you want to use, I mean, if it's going to be a perfect fit, why wouldn't you want to just use whatever it is that fits perfect and does the nice interpolation for you? Well, because this one, we have negative 0.375x to the 4th, which means the end behavior would look like that. And if there are situations in the real world where you're saying you can't just endlessly go down forever, that wouldn't be the best way to write this. That's not what's really happening in the real world. Then we've got to pick a different model, a model that doesn't have that happening. So it is best to take a look at the stat plot. And if you notice a pattern and you're saying this would be a better fit, even though the numbers might not come out perfect and give you that r of 1 or r squared of 1 in this case, then that's the model you use. And you have to use the brain over the calculator sometimes to go through these. And that's kind of what it says down here in this little box, is always try to pick a model. So look at the stat plot. Pick a model with the lowest possible bit rate. So there's 6 points. And you say, hey, 6 minus 1 is 5. I'm going to do quintic. Well, first of all, you're not going to find quintic on most of our calculators. But then you should say, you know what? Since it's degree 5 and degree 3's act the same, maybe I can just go with a cubic instead. Or maybe you graph them and you notice, hey, these all seem to be pretty linear here. I might be able to get a really straight line for this one and have a pretty good R value. So we don't just want to hand it over to the calculator. Do the subtraction and say this is going to work. We want to think about the model when we get going. So that was the end part of this last objective that we had up here, modeling polynomial functions, was to make sure that we could do the regression. So if on the test, and it'll be there, we tell you to do cubic regression or quartic regression, and you plug them in and you get us the model, show me your confidence level, 4, 3, 2, 1, 0. You just have that on there and you're graphing it. Not even graphing it, I should say. You're just plugging it in to get it. Okay, good. So some of you feeling much better about using your calculator than others. And I showed you this yesterday, but well, one person was absent for sure. So there it is. A few word problems there with, I'm sure there's boxes in that one. And then some regression. You know, I'm going to get you some candy partners, and we're going to start reviewing for this test.